Welcome to my sixth tutorial in statistical thinking, titled Making Statistical Decisions with Hypothesis Testing. In our last tutorial, we constructed and reasoned with confidence intervals as one approach to answer our statistical questions about the population parameter of interest. Another approach to making statistical decisions regarding the value of a population parameter is known as hypothesis testing. There is one key difference between this approach compared to a confidence interval. With a confidence interval, we began with no assumptions regarding the value of the population parameter. We reasoned with our sample statistic and the sampling distribution centered at the unknown value of the population parameter and tried to capture that value within our confidence interval. With hypothesis testing, we begin with an assumed value for the population parameter called the null hypothesized value, or simply the null value. We will calculate the probability of obtaining our sample statistic, or one even further from the null value, given the null value for the population is correct. This probability is known as the p-value. The null hypothesis is a statement regarding the currently accepted or status quo value for the population parameter. It could be the hypothesis stating the population mean height of men in the US is equal to the currently accepted value. It could be the hypothesis the true effect size or difference between two treatment means is zero in the population. It could be that a particular coin is fair. When it comes to researchers comparing treatments, it is reasonable to begin, before the data is collected, with the assumption that the treatments are equally effective. The aim of the researcher is to test that assumption. The researcher believes that their new treatment is more effective than placebo or a competitor's drug. They want to run a test on the data they will collect to see if they can find a statistical evidence that the true effect size is not equal to zero. The alternative hypothesis is a statement rejecting the null hypothesis. The alternative is our research hypothesis. It could be the hypothesis that the mean height of men in the US is not equal to the currently accepted value. It could be the hypothesis that the true effect size or difference between treatment means in the population is not zero. It could be that a particular coin is not fair. The data will provide the strength of the evidence against the null hypothesis in favor of the alternative hypothesis. We can think of the null hypothesis as analogous to the presumption of innocence at the beginning of a jury trial. The alternative hypothesis is analogous to the rejection of innocence in favor of a guilty verdict. The researcher is the prosecutor in the trial. No matter what the prosecutor believes, they have to respect the assumption of innocence, the null hypothesis, at the beginning of the trial, and work with the evidence to try and convince the jury that the defendant is guilty. Only when the evidence is beyond a reasonable doubt will the jury reject innocence in favor of guilt. If the evidence is not beyond a reasonable doubt, the jury will not say the defendant is innocent. The jury will simply say the defendant was found to be not guilty. Our statistical evidence is to be found in the data that we collect. Only when the statistical evidence is beyond a reasonable doubt will we reject the null hypothesis in favor of the alternative. If the statistical evidence is not beyond a reasonable doubt, we will not accept the null hypothesis. We will simply state that we have not found enough statistical evidence in favor of the alternative to reject the null hypothesis. Due to sampling variation, our sample statistic may deviate somewhat from the null value for the population parameter, and the null hypothesis could still be true. However, at some point, when the sample statistic deviates so far from the null value, we have to question the assumption that the null value is correct and decide whether or not to reject it. We have to decide where to draw the line that represents the border between sticking with the null hypothesis or rejecting it in favor of the alternative. If our sample statistic crosses that borderline, we have moved beyond what is considered a reasonable doubt. We will reject the null hypothesis and state we have found statistical evidence in favor of our alternative research hypothesis. The most commonly accepted borderline used for making this decision is when our sample statistic deviates from the null value for the population parameter by more than 2 standard errors. When this is the case, the sample statistic is considered too far from the null value to be simply due to sampling variation, given the null value is correct. We say that we have found an accepted level of statistical evidence in our data to reject the null hypothesis in favor of the alternative. Our results are considered statistically significant. There is a lot of discussion and debate in the scientific community regarding where the borderline should be drawn for making statistical decisions using hypothesis testing, which I discuss in depth in Chapter 8 of my book. We will begin to understand the reasoning of hypothesis testing through the example of the coin toss experiment. If a coin is fair, we'd expect to obtain a head 50% of the time we toss the coin, or 0.5 as a proportion. For example, if a coin is fair and we toss it 100 times, we'd expect 50 heads. However, we know that due to sampling variation, the number of heads we obtain could deviate somewhat from 50, and a coin could still be fair. The question is, at what number of heads obtained would we start to consider the possibility that the coin is not fair? If we get 55 heads out of 100 coin tosses, do we decide we have evidence that the coin is not fair? What if we get 65 or 70 heads out of 100 coin tosses? Do we decide we have evidence that the coin is not fair? Where do we draw the line in the sand between sticking with the assumption that the coin is fair or rejecting that assumption in favor of stating that the coin is not fair? We decide to run a hypothesis test to assess whether or not we can find statistical evidence that the coin is not fair or biased towards heads or tails. The null hypothesis is that the coin is fair, and the alternate hypothesis is that the coin is not fair. Due to sampling variation, we know we could get a sample proportion of heads that deviates somewhat from 0.5, even when the coin is fair. From the result of the essential limit theorem, we can calculate the range of possible sample proportions we expect based on the number of times we toss a fair coin. We decide to toss our coin 100 times and calculate the sample proportion of heads. If the coin is fair, we expect 95% of possible sample proportions of heads to be within 2 standard errors of 0.5. The standard error in this case is equal to 0.05. Based on 100 coin tosses, if the coin is fair, we expect 95% of possible sample proportions of heads to fall between 0.4 and 0.6. If our sample proportion of heads turns out to be outside this range of values, then the deviation of our sample proportion from 0.5 is considered statistically significant. It is unlikely to have been due to sampling variation alone, given the coin is fair. We can say that there is statistical evidence in our sample data that the coin is biased towards either heads or tails. In other words, when we toss a coin 100 times, if we get less than 40 heads or greater than 60 heads, we can say that it is highly unlikely that our coin is fair. If the coin is fair, obtaining a total number of heads more extreme than these values would happen only 5% of the time. We would expect only 1 out of every 20 experiments, or 5% of this kind, to result in a statistic that deviates so far from the null value for the population parameter. When our sample statistic is outside this range of values, we can choose between 2 possible scenarios when making a statistical decision regarding the value of the population parameter. For this example, we can decide that the coin is fair and say that we have just experienced an unusual chance event due to sampling variation. Or we can decide that we have found statistical evidence that the coin is biased. It is generally accepted that if the sample statistic deviates so far from the null value that will occur only 5% of the time or less, assuming the null value is correct, then the null hypothesis should be rejected in favor of the alternative hypothesis. Let's return to the height example from an earlier tutorial. Let's say you want to estimate the population mean height of male students at your college. You decide to select a random sample of 144 male students and measure their heights. The sample mean height you calculate from your data turns out to be 69.5 inches. As mentioned previously, according to the top Google search result, the currently accepted mean height of young men in the United States is equal to 70 inches. We wish to challenge this claim using hypothesis testing. Our null hypothesis states that the population mean height is equal to 70 inches, and our alternative hypothesis states that the population mean is not equal to 70 inches. By testing or challenging the claim that the population mean height is equal to 70 inches, we are stating that we are looking for statistical evidence using our sample data in favor of our alternative research hypothesis that the population mean height is not equal to 70 inches. As long as the necessary assumptions and conditions hold regarding the quality of our data, the central limit theorem states that the distribution of possible sample mean heights follows the normal distribution, centered at the population mean height. For hypothesis testing, we call the normal distribution of sample mean heights the normal model, or simply the model. Under the null hypothesis, we are assuming that the model is centered at 70 inches. The question is, what are the chances of obtaining our sample mean height given the null hypothesis is true that the population mean height is in fact 70 inches? If the population mean height is 70 inches, we expect 95% of sample mean heights, based on sample sizes of 144 men, to fall between 69.5 and 70.5 inches. Note that the standard error of the sample mean in this case is equal to 0.25 inches. If our sample mean height falls beyond these borderline values, then it is considered statistically significant. It is considered an unusual value given the null hypothesis is true. Our null hypothesis is rejected in favor of the alternative hypothesis. Our sample mean height of 69.5 inches, two standard errors below 70 inches, is exactly equal to the borderline value used for making statistical decisions. Our sample mean height is almost enough evidence to reject the null hypothesis in favor of the alternative. However, based on our criteria, it is not far enough away from the null value of 70 inches to reject this claim. We will formalize our decision making by calculating what is known as a p-value, a probability value, and explaining what it means in the context of this example. The grey shaded areas in the figure shown represent the p-value. The p-value is defined as the probability of getting the sample statistic we observed, or one more extreme, even further from the null value, given the null value for the population parameter is correct. In this example, the p-value is the probability of getting a sample mean height of 69.5 inches or less, or 70.5 inches or greater, given that the population mean height is equal to 70 inches. A sample mean height of 70.5 inches or greater would be just as much statistical evidence in favor of the alternative hypothesis as a sample mean height of 69.5 inches or less. We need to take both possibilities or probabilities into account when making statistical decisions using hypothesis testing. A sample statistic will deviate from the null value for the population parameter by more than two standard errors only 5% of the time. In other words, when our sample statistic is more than two standard errors away from the null value, the p-value will be less than 0.05. This borderline value, or line in the sand, of 0.05 is known as the level of significance. This is the most commonly accepted level of significance used in hypothesis testing. When our p-value is less than 0.05, we can say that we have found statistical evidence in our sample data to reject the null hypothesis in favor of the alternative hypothesis. Our results are considered statistically significant. Our p-value is exactly equal to 0.05 in this example and is therefore not less than the level of significance. We have almost found, but not quite, enough statistical evidence to reject the null hypothesis that the population mean height is equal to 70 inches. Since it is not less than 0.05, we fail to reject the null hypothesis. However, what this example illustrates is that if our sample data was only slightly different, maybe a couple more shorter men, we would have rejected the null hypothesis and claimed statistical significance. P-values are a convenient and much used way for making statistical decisions. Our entire analysis can be boiled down to one value, and if that value is less than 0.05, then we can say we have found statistical evidence in favor of our alternative hypothesis. Our results are considered to be statistically significant. How the p-value is used for making statistical decisions can give the illusion of certainty to a process that is inherently uncertain. If the sample size is small, then the variation in possible sample statistics around the unknown population parameter, measured using the standard error, can be quite large, meaning that there is still a lot of uncertainty regarding the value of the population parameter. A p-value does not reflect this uncertainty, whereas a confidence interval does. The p-value simply tells us the probability of obtaining the sample statistic we observed, or one more extreme, given the null hypothesis is true. The key takeaway from this discussion is that you should not try too hard to grasp the meaning of the p-value. It is a convenient calculation for making statistical decisions with hypothesis testing, but it is not an ideal one. We should simply think about the meaning of the p-value more loosely as an indication of the strength of the evidence in favor of the alternative hypothesis. Again, it should be pointed out that the validity of the p-value as a decision maker depends on the quality of the data that went into calculating it. In our next and final tutorial, we'll take all we have learned over the last few tutorials to question the quality of the statistical analysis proportion of research and the integrity of the researchers conducting it.